Okay, good morning, everybody. Today I will talk about different kind of energy. Yesterday we started talking about the work and the kinetic energy, then the power. These are kinds of energies. Today we'll continue and we'll know more about what is the work. Okay. Today we'll start talking about the potential energy. There's another kind of energies in physics. One of them is the potential energy. What is the meaning of the potential energy? We'll see that now. Yesterday we started talking about the kinetic energy by using one of our known equations. And we use this equation, V2 square is equal V1 square plus 2ax. Then we multiply it by the mass, then divide over 2. This is the work, because this is the force multiplied by x. From the work, we find the new kind of energy. Today we'll do the same thing. Assume that we have these two experiments. This is the first one. And we know how to deal with them. If we have two altitudes, we have here y2, this altitude, this building, and here is y1. We have a mass. At y2. The second experiment, we have this mass at y1. As we know, we have the gravity downward. We assume the positive direction upward. What we have also. The first experiment here, if we lift our mass to free fall like this, who is the actor? What is the reason that the mass goes downward? As we know, it is the gravity. So the motion of the mass is due gravity. So this work is done by gravity to move the object, because the mass is here, we lift it to move, then it has now a kinetic energy. If the mass moved from y2 to y1, from y2 to y1, so this is delta y, which is y1 minus y2 in this case. What is the work? The work is equal to F multiplied by delta y. What is the force in this case? It is the weight. It is the weight. We have the weight downward, which is mg. What is delta y? It is what? Y final minus y initial. Y final is y1 minus y2. This is the work. We can write it as two terms like this, which is equal to mg y1 minus mg y2. We know how to do that. What about the second experiment? We have y2, y1. Initially, we are at y1. What if we need to lift this object from y1 to y2? We don't need to have any acceleration. We have the weight, which is equal mg. Now look, we have the weight, we have the work. So I will write the weight as mg. I will not deal with it as or F gravity. Now W is for the work. Now, if I need to move the object with constant velocity means the acceleration is equal to 0. What does that mean? Okay. Means that total F in y direction, we are moving in y direction, is equal to 0. What is the forces now? What are the forces? We have mg downward. We need another force done by us to lift the object upward, plus F applied by us, it is upward, should be equal to 0 because the acceleration is 0. Why? Because Fy is equal to ma as ma in y direction as Newton's second law. In this case, I need the applied force is equal to minus mg, because if I move this to the opposite side, it will be negative. Okay, so the applied force, this is applied force, should be equal to mg. Okay, what is the work in this case? Done by the external applied force. It is simple, we cannot write it. It is W is equal to the applied force, which is mg, multiplied by delta y. Delta y, it is y final minus y initial. Okay. I'll put it here because I missed the theta part in the first question. Okay. F, the first part, the first experiment, F is downward, which is mg, downward. Delta y is downward. How much theta between them? Cosine theta. Theta in this case is 0. Cosine 0. Cosine 0 is 1. So it will not affect anything. This will stay the same. In this case, I have the work is equal to the applied force, which is upward. Delta y. It is delta y. Delta y is also upward. Okay. Cosine 0. But F applied is negative mg. This is mg. You can put negative mg delta y, cosine 0 is 1. Or you can put your applied force like this. The applied force is minus mg, which is mg to the negative part. If you now take mg and delta y, the sign, the theta between them is 180 or 2 pi or 1 pi, I'm sorry. So in this case, it will be mg cosine 180 as you see in the notes. It's the same. Okay. Now, it is equal to the work in the second case is equal to mg y2 minus y1 with negative sign. Because cosine 180 or negative mg, we have a negative sign. If we put the negative sign on the parenthesis, it will be mg y1 minus y2. Two terms, mg y1 minus mg y2. This is the work. The second case. This is the work. In the first case, they are the same. What is the meaning of that? The meaning of that, we have a new thing. We need to divide it again. Remember here, the work yesterday, we see that the work is equal to the change in kinetic energy, which is equal 1 over 2 m v2 square minus 1 over 2 m v1 square. Today, there's a difference. Look, we have the work, the both cases is the same thing, which is mg y1 minus mg y2. But the kinetic energy, 2 minus 1. What we need to do now, if we look at this, W is equal to mg y2 minus mg y1. We need to put minus sign for them. If we define mgy as a new quantity, this will be equal to negative the change of that quantity, which I name it U. Now, look, from before we defined kinetic energy is equal to 1/2 mv squared. Now we need to define the potential energy. U is equal to mg y. Look, we have the mass, we have the gravitational acceleration, we have the altitude. This potential energy comes from these quantities, which are the altitude, the position, and the gravity. Because of that, this potential energy named the gravitational potential energy. So we will name it UG. We will deal with another one. In our life, we have many potential energies. Now, any question about these derivations? If you remember some equations, I don't derive it. I didn't derive them. I will not derive them because there is no benefits from the derivation. But here, because we will solve examples using the work and the altitude and because of that, I show you the derivation. And because U is an energy, its units is joules. Any question about that? Okay, now in the second page, I have an example, a simple example. Now we need to compare between the work and the kinetic energy. And we will see also what is the kinetic energy again when we deal with the elastic kinetic energy. Okay, in the second page example, computer lift titanium from one. Yes, we need to lift mass 3 kilograms from, if this is 0, we need to lift it from y equal to 5 to y equal to 10. With constant velocity. We don't need any acceleration. That means the force we need to apply is equal to the weight, which is mg. Okay, what is the work? The work is equal to F dot delta y. Delta y, I use now the dot product as you see. Delta y is upward. The applied force will be equal to the negative mg, just as the second case. You can use F applied is negative mg, delta y as 10 minus 5, and cosine 0. Or you can use, as I solved it in the example, it is equal to mg, the applied force, 10 minus 5, cosine 180. So this is equal to M is given 3, G is almost 10 or 9.8. 10 minus 5 is 5. Cosine 180 is negative 1. So my work will be negative 147 joules. Because I lift the object from 5 to 10 by a force equal to the gravity force. Now I'm asking not about my force work. I am asking about the work done by gravity. The work done by gravity, it is Wg. It is negative. It is in the opposite side. The gravity is downward, and the work done and the motion done in the opposite direction of that force. Because of that, it will be negative. Now, if I need to ask about the change in potential energy. I can take, this is 5 meters, this is 10 meters. The potential energy U at 10 or U finally is equal to mg multiplied by y, which is 10. And U initially is equal to mg multiplied by 5, which is y initial. And this is y finally. I can solve two equations. But simply, we found now that the work done by gravity is equal to the negative potential energy done by that force. So it will be equal to the negative 147 joules, which is positive 147 joules. This is the change in potential energy. Now, in this case, if I ask you, if I lift this object to fall down from 5 meters, and I have a glass here, which is a strong glass, okay? From 5 meters and fall to that glass, it will break it or smash something to big pieces. But if I throw it from 10 meters, the effect will be bigger or smaller. It will be bigger, will smash it, okay? Smashing the cup to these pieces, then these pieces need more energy. Because it's smaller. We need more energy, right? These pieces appeared after falling from 10 meters. These pieces appeared after falling from 5 meters. Because of that, the object at 10 meters contains larger energy. Why? Because of its position. The word because of its position or because of its situation give us the name potential energy. It is a potential energy because of its position here. It's another potential energy because of its position here. Okay? And if the object is move again from 10 to 5, it will give us the same energy, which is 147. Because we put, when we lift it from here to here, we give it 147. If he move from here to here, he will give us 147. The nature is fair. The energy is conserved. If we give energy to a system, and the system needs to give that energy again, it will give the same energy. This thing give us a postulate or something like that, which means that the energy is conserved. The third page is talking about mechanical energy. The energy in physics has many shapes. We now see 2 or 3, I'm asking. We are dealing now with 3 shapes of energies. What are they? The first one is the core, it's energy. And we will see what is this energy, and the kinetic energy, and the potential energy. Then when we deal with the rotational motion, we have a rotational kinetic energy and potential energy. But all of them are energies have units of joule. Okay. The potential energy. We have many shapes of this potential energy. For an example, this is a battery. This is plus and this is a negative poles. Inside the battery, we have a chemical elements. Okay, so we have potential energy, but it is chemical. This chemical energy, if we have a wire and we have a speaker here, and we have a light, this potential energy will be converted to electrical potential energy. If we have also a solenoid here, you know, we will see a magnetic field. This magnetic field contains magnetic potential energy. The speaker will give us a sound. This sound is a mechanical and wave potential energy. The light here, it is an electromagnetic potential energy. So another potential energy inside the nucleus of the atom. We have the nuclear potential energy. Nuclear, which we use to generate electricity. So the potential energy, there's a potential energy in the light, which is electromagnetic potential energy, and so on. So the potential energy has too many shapes. The kinetic energy, just one shape, 1/2 mv squared, that's it. So this potential energy is stored, because it is chemical, stored in the interaction between elements. The the potential energy inside the nucleus stored in that nucleus. Because of that, it is hidden or stored or conserved potential energy in that situation. The work, as we know, it's the force multiplied by the distance between. In our course, we need to name one general kind of mechanical energy. We are dealing with mechanical energy. Mechanical energy. It is as a big system. Contains inside it a work, the kinetic energy, the potential energy, and the potential energy by its shapes, all of its shapes. Sometimes we have a frictional force. The frictional force will do a work due frictional force, which is a negative work in the opposite direction of the motion, and so on. All of this is equal to the mechanical energy, or E mechanical. You can name it as you like. And we have a plus sign between them. So, for example, if we have the work is equal to 5, the kinetic energy is 12, the potential energy is 7, and the work due frictional force is negative 1. How much the mechanical energy? Just add them together. 5 plus 12 plus 7, 24 minus 1, it's 23 joules. Our system contains energy 23 joules. If I go away for an hour and come back to this room and to this system, the energy will still the same, 23 joules, because it is conserved inside this system. The nature is a big system, but we will not deal with all of the nature, all of the universe. We will assume that we have this system, just a subsystem. And this system contains these energies, and these energies will stay the same during the lecture or during that problem, okay? Sometimes they say our system is not conserved because there is a leak here. This leak will make the frictional force to go out from it, which is a negative force, and the shape of this leaking, maybe it will be a heat in the engine. If we have an engine or the car, there is a heat will be distributed around the car because of the work done by the engine. Or a sound, for example, look here. I don't know if you can hear a sound, but there's a sound. This sound, now we hear the sound of the motors of the AC. We don't need to hear their sound. There is no benefits from their sounds. Because of that, the sound created is a lost energy. We don't need to lose this energy. Because of that, sometimes we can name our system non-conserved. A small example about what I'm talking about. And by this example, we will understand what is the work. If we have this system, in page number 4, and this system contains the mechanical energy or the total energy is equal to 100 joules. They need to be the same. This system is conserved. And inside our system, we have many boxes. Each box contains one shape of that energies. For example, this box contains the potential energy due to the heat. This box contains the energy due chemical energy. the battery, for example, and the system. This, because of photoelectric, there's a bulb in our system. Here also there is a gravitational effect in our system. Maybe it is an elevator, and this elevator change its position due to gravity, and there is the light in that elevator. There is a chemical interaction inside the elevator. I don't know what is it, and there is a heat in the ropes and the strings and the motor, and there is a kinetic energy because it is moving. It's an elevator. Okay. Assume that we have these quantities: 20 joules as a kinetic energy, 5 joules as potential energy, 30 joules as light, 30 joules as chemical energy, and 10 joules as heat energy. How much the total? 60, 70, 90, 95. Assume at beginning we have 10. All of the energies are if we add all of them, it will give us 100 joules, which is the total mechanical energy. But sometimes if we have take a photo, now we will see that we have 5 joules in the potential energy. Where is the 5 joules? Are they lost? Or maybe will be converted to a kinetic energy. Sometimes part from the potential energy will move to the kinetic energy. Sometimes the elevator change its velocity. Because of that, the light will not have a stable intensity. Then where's the energy change from part to part? The change in energy and the energy that moves from shape to shape, this thing we name it work. So the work is a shape of the energy, but it is the change. It is just like the money. When I need to buy something, I need to give it to the person. This is the change. It is the work. The work is a shape of energy, but it is the moving energy, which is required to convert energy from shape to shape. For example, now I have a chemical energy in my hand, my arm. I will convert it by a work to be a kinetic energy in the eraser, like this. So I did a work to convert chemical energy to mechanical energy. This is the work. Okay? It is the language to change the energy from shape to shape. What we have else? I will talk about the fifth point in page number 4, which is the elastic potential energy due spring. In the example, when I come to it, we'll deal with the kinetic potential energy. In our class, we'll deal with the kinetic energy and the potential energy. Potential energy due gravity and due spring force, which is the elastic. And we will not deal with the photoelectric potential energy or chemical or heat. But we will see how heat will be, we can deal with it. Okay, we have an example. Now, in general, in our lectures is shorter, will be shorter, and more example in it. Any question about energy and the definition of that, each kind of the energy? I want line. There is a homework on the previous lecture. I will, it's just 4 questions, as always. But I will add to them maybe 2 questions or 3 or 2 So it will be 6 questions or 7 with 1 extra. The 2 new questions is about the potential energy. So the homework for the energy, potential energy, the work, just 1 homework contains 6 or 7 questions. And you have open time to finish it. And please finish the previous homeworks. Just to don't put a pressure on you at the end of the semester. You have the time to do that, but do that as soon as possible. And finish this homework because we have an exam at the end of this week. There is a review also for that. Okay, what about our example now? Also, I'm sorry, always we have a building. There is a building everywhere. Okay. Where's the man? The height of this building is 60 meters. I am supposing that when we talk about the example, we are understanding what is the example. And we have many heights. 1, 2, 3, 4. Yes. 1, 2, 3, 4. 1, 2, 3, 4 points. At each point, 20 meters. So this is 20 meters. This is 40. This is 60. It's simple. And this is 0. What else? What is the mass? We have an object with mass equal to 5 kilograms. طيب. Start free fall from y1. That's y1. Okay. y1 is here. 2, y3, y4. With velocity v, v1 is equal to 0. Free fall. طيب. Compute the potential energy, the kinetic energy, the mechanical energy at each point. Yes, right. We need to find everything everywhere. And we don't have any frictional force. Any question how? What does the question mean? Huh? Let us start with point number 1. The main relation now, we need to write it always. The mechanical energy is equal to kinetic energy plus potential energy. Our potential energy is just a gravitational potential energy. If we have another potential energy, for example, elastic potential energy, we need to put it. Because this potential energy is 2 parts. But we have just the gravitational potential energy. Okay. At point number 1, the mechanical energy at point number 1 is equal to the kinetic energy and the potential energy at point number 1. Okay. If you like to compute everything alone, every term alone, separately, you can do that. If you like to do them all together, you are free to do that. So the mechanical energy at the first point, the kinetic energy, 1/2 m v1 squared plus m g y1. This is very, very simple. The kinetic energy is given. The potential energy is given. I need to use them at the first point. Okay, this is equal to the half. It's just the half. The mass is 5. The velocity at the first point is 0 squared plus the mass is 5. G is 9.8. I like to use 10, but I have to teach you the right magnitude, which is y1 is 60, right? This will give us 0 plus this thing. It will be the mechanical energy will be equal to 2,940 joules. The kinetic energy is equal to 0. The kinetic energy is 0. The potential energy is equal to 2,940. All of the energy is a potential energy. Now at point 2, the mechanical energy at point number 2 should be equal to the mechanical energy at point number 1, which is equal to 2,940 joules should be equal to the kinetic energy 1 over 2, 5 multiplied by V2 squared. I don't know how much V2. Plus the potential energy at that point. I can use all of this term as kinetic energy too. It's okay. I'll use it like this. Plus M, the potential energy at point number 2. It is 5 multiplied by the altitude, which is 40 by G also, 9.8. So 2,940 is equal to the kinetic energy at point number 2 plus that number, which is at point number 2, the potential energy is 1,960 joules. What is the kinetic energy in this case? It is this minus that. So the kinetic energy is equal to 2,940 minus 1,960. It will be equal to 980 joules. This is the kinetic energy. I will talk about them. Now, what about the third point? I'll remove this because we already know everything about them. The third point, the mechanical energy is always the same. We don't need to name the mechanical energy by 1, 2, 3, and so on, because it is the same. The mechanical energy is always 2,940 joules. It is equal to the kinetic energy at point number 3 plus the potential energy at point number 3 now, which is M or 5 kilograms, 9.8, which is G, and the altitude at the third point, which is 20 meters. From that, kinetic energy is equal to 2,940 minus the potential energy at the third point, which is 980 joules, which is equal to, just replaced is the 1960 joules. This is the kinetic energy at point number 3. The point number 4, it is not total trivia. We have at point number 4, the mechanical energy is equal to the same thing, 940 40 with 2,000 joules. This is equal to the kinetic energy at point number 4 plus the potential energy at point number 4. The potential energy, it is mgy. How much y at point number 4? How much y, the altitude? It was 60, 40, 20, then 0. So the potential energy at the fourth point is equal to 0. The mechanical energy, all of it, is equal to the kinetic energy. Look, we have a mechanical energy, 2,940. It was totally potential energy. Then, by starting moving, because we don't have velocity, we don't have kinetic energy. Because the object starts accelerated, the velocity starts increasing. The velocity starts increasing, the kinetic energy starts increasing. Until the kinetic energy consume or will be all the mechanical energy at y equals 0. Okay? We can draw a graph, talk about this thing. And I suppose the graphs should be understood to you by dealing with the graphs in your life and in the lab. This is the building, and this is our graph. This is the mechanical energy, or the kinetic energy, and not or, and the potential energy. Our total mechanical energy is, this is the total mechanical energy. It is equal to 2,940 joules. Here, we can put y, which is the position. We have 4 positions, 4 situations, at 0, at 60, this is 20, and this is 40. We have 4 points. We have a mechanical energy, we have a kinetic energy, we have a potential energy. At the beginning, now I need to draw the potential energy, and I draw it as point, as square point. The potential energy, initially, how much it was? Here, it was the maximum value of the energy, which is here, 2,940. And we have the values, 1960. And we have 980, right? And we have the 0. At point, no, at y equal to 0, the potential energy is 0. The potential energy is a circle. The potential energy is a circle. At y equals 0, the potential energy is 0. At y equals 60, the potential energy is the maximum value. At y equal 40, the potential energy is equal to 1,960 at this point. At point 20 meters, potential energy is equal to 980. What about the kinetic energy? The kinetic energy will be a square. At 60 meters at the top of the building, the kinetic energy is 0. Then the kinetic energy starts increasing at 40 meters, then it continues increasing. Then the maximum value of the kinetic energy at x equal to 0. At each point, if you add the square to the circle, it will give us 2,940. The square at 0, this is at the top. If you add this to this, it will give you all of this. Move this to here, it will give you the total energy. Because of that, our mechanical energy is conserved. It is conserved and the constant, the slope of this line is 0. There's no change in it. And the kinetic and the potential energy are changing. Because what? Because the position is changing and the velocity is changing. Any question about this? Previously, I asked you to find the velocity. V final, V2 is equal to V1 plus 18. You need to use these equations. But when we use the energy technique, we can use the velocity anywhere. For example, at point number 1, we have the kinetic energy equal to 0, which is equal to 1 over 2. M is equal to 5. V1 squared equal to 0. That means V1 is equal to the square root of the 0, which is 0. What about point 2? Kinetic energy is equal to 980, and it is equal to 1/2 multiplied by 5. V, this is at point 1, this is at point 2. This is V2 squared. So V2 will be equal to the square root of 2 over 5 multiplied by 980. You can't find it. You will find two values, plus and minus. Which one we need to use? Is it the positive or the negative one? Our direction downward. The positive direction is upward. In this case, we need to use the negative sign because the direction is downward. What about V3? Kinetic energy at point number 3 is equal to 1,960. This will be equal to 1/2. The mass is 5. V3 squared. Okay, V3 is equal to the negative root of 2 over 5, 1960 meters per second. The negative side because we are going downward. And the same for the fourth velocity. As you see, we are not using this equation, for example. V2 is equal to V1 plus AT, or V2 squared is equal to V1 squared plus 2AY or AX, or X equal to something. We don't use these equations. And in this case also, we don't care about the acceleration. If the acceleration is not constant, here in these equations, we need the acceleration to be constant. But here, if the acceleration is not constant, we don't care about it. Okay? So in our lecture, when we were young in our course, we just deal with velocity, acceleration, time, and that's it. And X. These are the equations of motion. We are young. Now, then we develop ourselves. We start dealing with Newton's law. Okay, we use the mass. Now we are older, we have our experience. We are dealing with work, energy theory. We are here now. I think we need to deal with the momentum and the collisions, but it's the same. This is the top of our study. Okay, work, energy theory. This is the top of our techniques. These are primary techniques. These are better. This is the best. Even in graduate studies, we deal with this. Work, energy theory. We don't care about the acceleration to be constant or not. We can deal with any frictional force also. Any question about that? I will talk now about elastic potential energy. Just take a rest. We have the time. I will finish before the lecture and we are free after that. The second part, the next week, we will deal with the rotational motion. In the rotational motion, we will repeat our study again. And I will remind you by that. Our study now is linear. Linear motion means a motion in a straight line. We will deal later with rotational motion. We will start again from here to here. That's it. Now we need to remember that the work is equal to the change kinetic energy, which is equal to kinetic energy 2 minus kinetic energy 1. And the work is equal to the negative change. This is delta, means the change. The potential energy means U1 minus U2. We have a minus sign. And the mechanical energy is equal to the kinetic energy plus the potential energy. This potential energy sometimes plus any other work. If you remember from the books, we have a work jump from type to type of energy. We have a work from any other source. This potential energy may be just one shape as gravitational. Maybe it is the second shape we will deal with, which is the elastic. So the mechanical energy will be the kinetic energy plus the potential energy due gravity plus the potential energy due a spring force or elastic force. Here, the work is equal to F multiplied by X by cosine theta. We need to cheat from that when we solve the example. The kinetic energy is equal to half mv squared. The potential energy due gravity is equal to mg y. Y is the altitude due gravity. We need always to find our or to assume our origin. Now we have the elastic potential energy. From before, we know that Hawkes force, which is equal to minus K multiplied by X. X is the compression distance for the spring. I will not derive the hooks or the elastic potential energy, it will be 1/2 K x squared. That's it. K is the same K, x squared is the same compression distance. That's it. So the potential energy due to the spring is 1/2 K x squared. K is the spring constant. If the spring is light, it is easy to move it, then K is small. If the spring is need more force to push it or expand it, then K is big. Any question about this? We will start now for maybe a long example. But we will apply everything in that example. We will apply the kinetic energy, the potential energy, the mechanical energy. This is a comprehensive example. You can assume it as a review. Again, today we deal with the two quantities, new quantities in physics. Potential energy due gravity, potential energy due elastic, and the mechanical energy. Just our lectures, just quantities and applications. Now we talk about the elastic potential energy. Now we need to put an application. Before I forget, we know that this is a spring. It is a linear spring. We can push it, we can expand it. Also, we have this spring. We can push it and expand it, but rotationally in angle. The application on this spring, it is inside the clocks. Okay, you can see it sometimes if your block is transparent, has transparent walls. Also, the wall in our house, when we rotate it, then it come back to its position. It contains a spring like that. In elevators, in the elevator well, this room, there is a spring downward because when the elevator go down, it will not be stopped by the ground. It will be stopped by a spring. You know that springs are always used in our life. It depends also. This spring, when we push this spring by a force, maybe this force, maybe this is our initial situation for the spring without any expansion or compression. We apply a force, maybe this force, it's a box, maybe it's a box with a weight mg downward. It will push the spring downward. If we remove this force, then the spring will expand again. And if there is anything here, if I push the spring here and I put some mass and I release it, then the mass will be released by a kinetic energy, by a velocity. Then we have kinetic energy. This kinetic energy, it's energy. From where it comes? It comes from the energy stored in the spring situation. The spring situation gives us a potential energy. We use this also in the bow. We have a string. When we pull it with this rope, a rope or something like that. When we release it, the potential energy from the elastic potential energy will be given to this rope to be as a kinetic energy because it has a velocity now. So the potential energy or the elastic potential energy is used many times in our life. Now I'll go again to the example. We have this system. We don't have any frictional force. This is 0 point and the maximum altitude is 3 meters. So this is point number 1. Almost we need to name the positions. This is point number 2. And we have a spring here. We have a point number 3 here. The spring, the mass. Initially, we have the mass at altitude y=3. We release it. Then it will start moving without friction. It will come to this track. It will come to the spring. It will push the spring. So we have a change in length. We have x. At this point, this is point 4. When the spring is pushed, okay? The spring has K. It is equal to how much? 120 newtons per meter, okay? The mass is equal to 5 kilograms. Small numbers, easy numbers, just to understand the physics. And y, at each point, how much y? y2 is equal to y3 is equal to y4. How much? It is 0 at the 0 level. Okay, what we need to find? Find U1, K1, mechanical energy. Find everything everywhere. And the spring compression. Find X also. Okay. At point number 1, just as we did in the building case. At point number 1, we have the mechanical energy. We don't need to name M1, M2, M3 because it is the same. Is equal to the kinetic energy at point number 1 plus the potential energy at point number 1. And this potential energy due gravity. So due gravity 1 plus we have another potential energy. Potential energy, elastic potential energy at point number 1. It is E. Okay. We don't have any other work. Work from other forces, for example, frictional force, we don't have. We just have 3 terms. Okay. The mechanical energy is equal to the kinetic energy, 1/2. The mass is 5 again. The velocity, it was 0 squared. We don't have velocity there because V1 is equal to 0. It's a free fall. Plus the potential energy, mgh, mgy or h. H is the height. M is 5. G is 9.8. Y is a 3. Plus the elastic potential energy. It is 1/2. 120. How much the compression now? Initially, how much the compression? It is 0. We don't have any compression or expansion. This will be multiplied by 0. So the potential energy due to the spring is zero. The kinetic energy is zero. The mechanical energy will be equal to zero plus this thing, which is equal to 147, which is a good number, plus zero. So the mechanical energy now is 147. It's always the same. We need to move this to the second point. At point number 2, we have the same relation, but at point number 2. So our mechanical energy is equal to 147, and it is equal to kinetic energy at point number 2, plus the potential energy, mg2. How much is it here? How much the potential energy here? Can't tell me. It is mgy. How much y? It is 0. So it's right. 0. The potential energy due to gravity is 0. Plus, how much the potential energy due to the spring? There is no compression. It is 0. So our kinetic energy here is equal totally to. So kinetic energy at the second point, it is equal to 147 joules. It's simple. What about point number 3? It is the same. Mechanical energy is equal to 147, which is equal to the potential kinetic energy at point number 3, plus the potential energy at point number 3. The altitude is 0, the same 0. How is the compression of the spring? It is 0. So it is 0 plus 0. This is 0 due gravity. This is 0 due elastic. Gravity, elastic. So the kinetic energy again at this point is the same. We don't have any loss of the velocity. We don't have any acceleration or deceleration because we don't have any friction force. Now, what about the fourth point? At the fourth point, the force pushed the spring, the maximum push, the maximum distance. Then at maximum distance, remember the projectile motion at the maximum y, the velocity equal to 0. Remember that at maximum distance. Here we have a maximum distance. What is the velocity at maximum distance? This is at point 4. The mechanical energy, it is still 147, is equal to the kinetic energy, which is 1/2 5 V4 squared. Plus, how much the potential energy here? Due gravity. It is 0. Gravity. We are the same altitude. What about the elastic potential energy? Okay, it is 1/2 K x squared. K is given. X, we don't know X how much, but we can find it. What is the velocity at this point? At the maximum point, the velocity is 0. After this pushing, the object will repel again to the opposite direction. But at the maximum distance, this is 0. So the kinetic energy 4 is equal to 0. So all of our mechanical energy is equal to the elastic potential energy. If you ask about the elastic potential energy, now it is equal to 147. What is the X? Yes, Alan. It's simple. I'll show you. Where is it? I'll put it here. U elastic is equal to 147, which is equal to, that is the relation, 1/2 120 x squared. So x is equal to the square root of something. This with this, it will be 60. It is 147 over 60. This will be equal to positive or negative. X, sometimes we expand the spring, it will be positive X. If we push it, it's a negative X. But in general, we need X. We don't care about positive or negative, but we can understand the sign, the meaning of the sign. Okay? X in this case will be, it will be Aha. .495, I think, meters. It is 49 centimeters, just like this. The spring will be pushed like this. Maybe it is a long spring and it will be pushed by 1950, half a meter. So this is X. Positive or negative, I don't care, because I know the meaning of that. If I suppose this is the positive direction, then it is positive. If this is the negative direction, then it is the negative. It's okay. Any question about this example? Hello? We don't have any frictional force. Take care about this. We have the same example now, I think, but with the existence of a frictional force, but without the spring. I can add a spring. I can also add a frictional surface there. It is not more complicated. Just I need one more step and one more term here. I need the work done by the frictional force, just like that. Just one more step. This is physics. There's no difficulties. Just add new term for any new thing or any new property in your system. I'll keep it, but because I'll lose everything. Just we don't have the spring, we have the frictional force surface. The altitude is 6 meters. There's an interest in the numerical values. The mass is 10, just multiplied by 2. So at point number 1, y is equal to 0. This is point number 2. The mass is 10. The velocity initially is equal to 0 meter per second. We have this surface. Then at this point, the surface is not smooth anymore. This is point number 2. This is point number 3. And this is point number 4. The object starts moving, sliding, come to this point before the tough surface, then start moving and stop after 10 meters. Its velocity here after stopping V4 equal to 0, just like the spring, but we have a frictional force now. Now the mechanical energy, we have the kinetic energy, we have the potential due gravity. We don't have any elastic potential, we don't need it. We have the work done by the frictional force. The work is done Fx, which is the distance cosine theta. That's it. We need to do that again. Let us start with the first point. The mechanical energy is equal to the kinetic energy. It's zero because the velocity is zero. I will not write it again and again, and you can do that. The kinetic energy, zero. This is the kinetic energy. Plus the potential energy due to gravity. It is M, which is 10, multiplied by G, which is 9.8, multiplied by Y at that point, which is 6. How much the frictional force now? Or the frictional load? Nothing, zero. So my mechanical energy always is equal to this. How much is? It is 588 joules. Point number 2. Yes, sir. It is more simple, just like what we did before. The mechanical energy is equal to 588. It is equal to the kinetic energy at point number 2. Take care. We can find the velocity in the previous example also here, but we didn't do that. Plus, how much the potential energy due gravity? Because the altitude is zero, the potential is zero. How much the work done by the frictional force? It is also zero. We don't have any frictional force here. So our kinetic energy at point number 2 is equal to the total mechanical energy, 588. It is also equal to the kinetic energy at point number 3, right? Nothing changed. We don't have any frictional force between here and here. We don't have any change in altitude. Now I need to talk about the last position. At point number 4, it is simple. The mechanical energy at point number 4, it is still 588. It is equal to the kinetic energy at point number 4. How much is it? Please answer me online. I'm waiting. How much the kinetic energy at point number 4? Look at the velocity there. Nothing. The velocity is zero. The kinetic energy will be zero. So the kinetic energy will be zero. So we have zero kinetic energy. Plus, how much the potential energy? It is at altitude zero. So we have zero altitude gravitational potential energy. What is the work done by the force? We have frictional force. This is the work done by frictional force. So the work done by the frictional force is equal to the total mechanical energy. It consumes everything. So the work done by the frictional force is equal to 588, which is equal to the force, frictional force, multiplied by x, multiplied by cosine theta. We know that. I'll do it here. So now we have F frictional force multiplied by x. X is 10. Cosine theta. You can tell me how much theta. The frictional force to this direction. X to this direction. This is theta. It is pi or 180 degrees. So cosine 180, it is equal to 588. This is negative. This is 10. This is negative 1. So the frictional force is equal to 588 over negative 10. It will be negative 558.8. The units of the force is in Newton. It is negative force. the frictional force has a negative magnitude to the opposite direction. If you need to find its work again, this is the work, 588. It is a loss in energy. It's a missing energy. Now, if I need to teach you something, if we have two systems, this is the first system, and this is the second system. And this is our system. This is the frictional force. Who can tell me how this frictional force will be observed by us? Maybe it will be a sound, because the object moving on the surface. Maybe it is a heat, so it will be like a heat. So it will be as a potential energy, as heat potential energy, or sound energy, right? If our experiment, this experiment is in a closed system, closed laboratory, then the heat energy and the sound energy will stay inside our system. In this case, our system is closed, okay? And it is conserved because the heat will stay inside our system. The sound will stay inside. But if we do this experiment outside, then the heat will go outside and the sound will spread outside to the universe. Then our system will be non-conserved system. Okay? So the frictional force here will be observed as a heat energy or sound energy or any other energy. Any question about this question, example? What if I ask you to find the mu k, which is the friction coefficient? It's simple. As you see here, we find F, but we know it is equal to mu k multiplied by the normal force, which is equal to the mu k. The normal force is mg. We need to find the mu k. This is known. Mg known. We just need to find this. It will be equal, I think, to 0.6 unitless. Page number 13. I talk about it, just the energy will convert from shade to shade. And this is another final simple example about this thing, which is the change in energy. If I asked you in the exam, I'll try to put this question. It is a good question. If we have an elevator, this is elevator well. Initially, the elevator has a potential energy, which is the total mechanical energy due gravity, is equal, for example, 25,000 joules. Then this elevator fall down, free fall, and there is a spring, a huge spring. In you can see that in the YouTube already. And the elevator push the spring and then jump again. By its jump, when it's jump again, its kinetic energy will be, for example, 24,000 joules. It will not jump by the same, maybe also less than this. it will not jump by 25 joules, because when it falls to this direction, at this point before hitting the spring, it will be 25,000 joules kinetic energy. Kinetic energy before. But kinetic energy after will be less than 25,000. Maybe it is less than this. I got this in the example, but it will be less than this. I'm asking you, is our system conserve the energy? The answer is no, because we lost 1,000 joules. Where are these 1,000 joules? There will be a heat on the spring body. Maybe there is a sound. Can you understand that? After that, you can measure the temperature of that spring, and you will find it is higher. It is hotter. You can do that. Use any spring and do it many times like this, and measure its temperature. It will be warmer, not hotter. And that's it for today. Any question about today's lecture? We finish it. We still have 30 minutes. I have a ready review for the previous and this lecture. We need to study tomorrow and the day after tomorrow. We need to study the momentum and the impulse and the collisions. We have elastic and inelastic collisions. And then we will be ready for the exam, the next exam. I will put the review as videos on my page again, because I don't need to solve everything here. You can see that later. And as you see, we have many examples. Any questions? Again, if not, then I will end the meeting today. And good luck. Assalamu alaikum.